your afternoon looks like. Have you checked this out?
I did. I think there's a couple meetings on there. I was just gonna just to like avoid it turning off.
We wait the Harvard 7 minutes.
Is that the standard?
Yeah, we do. We'll wait a few more minutes.
Sounds good.
In the meantime, maybe we can. Do you have to turn on some lights or?
I think the booths that they look at.
Okay. Yeah, we'll start in the queue, so maybe, yeah. All right, let's get to it.
Okay.
I'm gonna grab the mic. Okay, so today, can you hear me? Working?
Yeah.
Okay. So today we're fortunate to have Caitlin Witt visit us. Caitlin obtained her PhD at West Virginia University in 2022 and has since been a Sierra Adler postdoctoral fellow. She's also very involved in the NANOGrav experiment, and I suspect we'll be hearing a lot about this in the next 25 minutes. So thank you.
Okay, hello. Okay, I can hear the mic is on. Excellent. Thank you. So yeah, Magda basically said it all. Hello, I'm Caitlin. Feel free to just like yell at me throughout the talk. They told me aim for 25 and 25, so I kept it short. So very happy to take questions at the end, throughout. Just like wave and stop me, and if I don't see you, just yell at me. So today, like Magda said, I thought it would be a nice opportunity to give you all not only an overview of the NANOGrav experiment, like we've been giving at many talks over the last 15 years or so, but this is a special year because we've recently made some rather large discoveries and announcements that we're finally able to talk about. So today I'm going to be talking about not just pulsar timing, but also the gravitational wave background, and briefly at the end, a look forward to beyond. So I always like to start these talks with an overview look of what the gravitational wave spectrum actually looks like. Because many of us, as we hear about gravitational wave detections now in the era of LIGO, where we're getting all of these wonderful binary black hole detections, double neutron star detections, it's important to remember that that is really only a small portion of the spectrum that ground-based detectors like LIGO can see. And there are many more types of gravitational waves out there. And here I'm showing 3 typical experiments. There are others that may come in the future or may expand these boundaries a little bit depending on what we're looking at. But in context of binary black holes especially, right here, this is the window that we've really seen in so far, about 3 orders of magnitude in frequency space. Eventually, we just got the exciting news that LISA has been adopted by ESA. So eventually, we will have a similar laser-based gravitational wave detector in space that can see things like intermediate mass black holes or MREs, or even the very end merger stages of supermassive black hole binaries. But that, again, only covers a few orders of magnitude. So down even lower, where things like stably orbiting supermassive black hole binaries lie, or even a gravitational wave background of those low-frequency gravitational waves, there's only one type of detector that can actually see that low, and that is a pulsar timing array, where we're looking at these naturally occurring objects to extend our baselines longer than what we can fit on the Earth, even longer than what we can fit within the solar system with a launched mission, to actually make a gravitational wave detector the size of a galaxy with these naturally occurring objects that we can see with radio telescopes. So I would be remiss if I gave a pulsar timing talk and didn't make everybody learn a little bit about timing pulsars, even though that is not my area of expertise. It's important to remember. The general idea here is that we observe pulsars very, very regularly, and these things are emitting a beam of radiation from their magnetic poles. So as they orbit, if those poles are misaligned, the idea is that as that beam sweeps across our line of sight, the little patch of space will get brighter in radio. So that's why we show over time these like steady, faint, 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 pulse, pulse. We can time these when these pulses actually arrive at Earth, akin to the ticking of a clock, hence pulsar timing. So if we are able to model our pulsars perfectly accurately, and the black line here representing the model perfectly matches the gray data that we get at our radio telescope, we have accounted for everything that exists, from the pulsar to the line of sight to the Earth. We know exactly when those pulses are going to arrive. Of course, these are naturally occurring objects. All of them are moving, all of them are rumbling, all of them are doing weird things that we don't like to think about. So that model will never actually match up to reality, unfortunately. So this is where we look in this what we call residual space. We subtract the model from the data, and in that, we are able to look for any differences from our model to our data. So an ideally timed pulsar will have these perfectly flat residuals, maybe with some Gaussian white noise, but any differences from that is where we actually want to look and see if there are timing effects. That may include things like the effects of the interstellar medium. It might include things like the orbital motion of the pulsar, or it might include some external effects. Spoiler, maybe some gravitational waves. So I'm a part of the NANOGrav collaboration. I also like to be sure I show that NANOGrav is not only a pulsar timing array, it's also a group of people who take that pulsar data, they time the pulsars, they observe them, they make the models. We make the gravitational wave models, we run the supercomputers to actually both reduce that data and search for gravitational waves, and then we tell everybody what it actually means. So here's all of our smiling faces as of probably 5 years ago, so I should really make us take a new picture someday. And if anybody is able to find me in this picture before I move on, I will buy you a coffee later.
On the left.
Nope. Good try, though. Okay. So NANOGrav has been timing pulsars for the last over 15 years now, and we recently released our 15-year data set. And so here is a representation of every single observation that has gone into this data set. And you'll see that it's inclusive of the previous data set. So once data has been observed and reduced and put into the data set, it more or less will be there forever. Every once in a while, outliers are removed, and that's done recursively. But you can see the 5-year data set, we started with 10 to 13 pulsars. The 9-year data set, we added more. The 11-year, the 12.5-year, we had 68 pulsars. And then now, here in 2020, in the 15-year data set, now we have 68.
Are the additions more distant, or what's?
Yes. So generally, we are looking for pulsars all the time. So generally, the ones that are added later, they could be a little bit dimmer, so maybe more distant, maybe slightly less high signal to noise, so they weren't discovered as soon. Maybe we needed more time to actually solve their timing parameters. Some of them are in more or less complex orbits that we needed more time to actually reduce them. We've actually had more pulsar searches come online, so there are wonderful pulsar searching machines like the CHIME telescope and FAST that can then send those discoveries to our telescope, where once we know where to look, we can gain more sensitivity than in the search mode data. Things like that. So yes, and also other effects. So the other thing I wanted to point out is that the color bar representing all these observations can actually tell us which timing system these pulsars were observed with. So all of the green points were logically observed with the Green Bank telescope. I believe the purple and blue points were all observed with Arecibo. And then now here at the end, we're also starting to observe with VLA. And in the next data set, we'll also be observing with CHIME. So we're adding systems all the time as well to expand our sky coverage, expand our sensitivity, and expand our observation cadence. And we can tell based on when some certain interruptions in this plot are, more or less what's happening at the system. So this scheduling, because it relies on our cadence and our regular observations, that's sort of what will set the limits of our observations and our sensitivity to gravitational waves. We need to observe often, and we need to observe for a long time span. So the general idea, as I said before, as we are looking in our residual space and we are timing the times of arrival of our pulsars, those ticks of the clock, as the gravitational wave passes, it'll stretch and contract the space-time that's existing between us here on Earth and us at the pulsar. So what we need to account for is the delay time that it takes for those pulses to reach us that is not accounted for in the pulsar model. So there's a few ways to describe this, and I find it helpful to build up from a picture of a single monochromatic gravitational wave. For example, from a single supermassive black hole binary. They're slowly orbiting, they're slowly evolving. Here I'm showing one that's being emitted from the center of the screen, and as time goes on, we can see the effects on the residuals of 3 different pulsars, a red one, a yellow one, and a blue one. And you can see, depending on where on their line of sight, they're affected more or less depending on their proximity to that binary on the sky. But we see this slow, steady change, this slow perturbation that is continuous. Yeah?
What would be the vertical scale in that? What is the change in that?
It depends on the pulsar. This is a very large one, because you can see there's basically no white noise in there. It's on the order of nanoseconds. So we have to time these things really, really accurately and get out all of the interstellar effects to actually pick these signals out. And this is part of why we need so many pulsars. It's because that signal will build as we can add them together, rather than just looking for 1 nanosecond delay in one pulsar. Finding a small delay with a small amount of evidence in many pulsars will be able to build up our confidence.
So I have it clear, if you're talking about a nanosecond difference.
Yes.
being
Vertical,
drawn
yeah.
vertically
Yeah.
Over years.
Over years, over decades.
Wow.
Yeah. Thank you. Okay, so single black hole picture. Okay, the important thing that I like to remind everyone, now that we have our picture in our minds, is that we certainly hope that there is not just one supermassive black hole binary in the universe. We think these things are something that is very common to the evolution of galaxies and exist throughout time and space. So while we might be able to see one particularly large supermassive black hole binary maybe close to us as one of those single continuous waves, we need to remember that these things are all emitting over top of each other all the time. And in fact, we think that there are so many of them that there's, in fact, a gravitational wave background from all the supermassive black hole binaries emitting together over top of each other. However, we again think there are so many of them, and we know that they are not affecting all of space equally, that we actually model this as a noise process, rather than trying to deconvolve all of those periodic signals into their individual binary sources. So when we are looking for gravitational waves from many sources, we model this as a stochastic gravitational wave background, which we used, I'll quote the description of a Hellings and Downs correlated common spectrum red noise process, which is a mouthful, and I will break down for everyone, because one of my goals from this talk is to have everyone come away from this talk with an intuitive understanding of not only what the background is, but how we look for it. So, but we can see, if anybody is looking on the sky, you can see our same red, blue, and yellow pulsars are sensitive to gravitational waves where they are in the sky, but there are instead so many sinusoids going into the signal, we can no longer by eye deconvolve all of the 200 frequencies and masses and amplitudes that are going into these signals. It's instead easier to model them as a red noise signal. So, first thing being the spectrum. When we're talking about this common spectrum, it's probably very familiar. A red noise spectrum is something with maybe a power loss spectrum that is stronger at low frequencies rather than high frequencies. This is why we call it red. The general idea here being that we think there are lots of gravitational waves emitting at lower frequencies. These have a longer residence time, they're evolving slower, so they tend to pile up at those low frequencies, hence a stronger signal overall. At the higher frequencies, these things evolve fast, even though they're strong. So they move out of these bins much faster. So this overall sum signal is generally weaker, which is why we end up with this very distinctive negative power loss slope. And this power law is actually what we're going to look at very closely when we're trying to determine the source of a gravitational wave background. So a background from supermassive black hole binaries has a very distinctive slope if it's driven solely by gravitational wave radiation. Strain goes like f to the minus 2/3. But there also might be some other effects we might look for. We might look for something like a turnover. That might indicate that something like gas evolution or some other like stellar interactions are driving the binaries to move faster through these early stages. So that's something that can really tell us something about the astrophysics beyond just the existence of gravitational waves and what they are. That will help us learn about binaries themselves. We may look for changes in this spectrum that will tell us like how these binaries are actually evolving. Is it binaries? Is it something else causing this background? I'll get into that in a little bit. Or we might look for deviations from this power law. Maybe there's a spike at some frequency that might tell us maybe to take a little bit of an extra look in that frequency bin. So the next thing to think about is the actual correlations themselves. And this is the thing that takes a little bit of thinking to grasp. So we have this red noise process going on over time. And if we actually deconvolve those timing residuals, we'll see that there are actually some spatial correlations between, if we, for example, look at the pair of the yellow and red pulsar. We'll see that as we look at the correlations between these actual time series, we will get, for example, a correlation function that relates to how far apart they are on the sky. If we then look at the red and the blue pulsar as a pair and the yellow and blue pulsar as a pair, we will be able to slowly build up this correlation pattern of how the pulsars relate across the sky. There are a few different ways that we could model this. For gravitational waves, it's been shown that they will have this very distinctive pattern that is 1/2 correlated for pulsars that are very close together, anti-correlated for pulsars that are 90 or so degrees apart, and then a little bit correlated for pulsars that are 180 degrees apart, so on opposite sides of the sky. That's something we would not expect for a monopole signal or a dipole signal. It needs to come from a quadrupole, which is why this is distinctive for gravitational wave radiation. So this plus the red noise process are what we are looking for to look for a gravitational wave background. Okay, so previously, NANOGrav's data sets, as we've built them up, we've also looked for gravitational waves along the way. For a long time, we were just setting up our limits and saying, this is how sensitive we are to gravitational waves. We know they must be weaker than at least this limit. In the 12.5-year data set, for the very first time, we started seeing a red noise process. So you can see here, the gray violins here are basically showing the delay offset in each of those frequency bins. And we can see that we're starting to see one of these power law deviations at the lowest frequencies. However, we needed more time span to actually extend this frequency baseline lower and lower. And then we also needed more observations to actually see if there were any correlations. So in the 12.5-year data set, we did not have any evidence for correlations. Yeah?
How am I supposed to relate this delay, this log delay, to the characteristic strain you showed on the...
Yeah, that basically is just a reformatting. We can see it in seconds. It's maybe a more natural unit. Trying to remember the exact relation, and I don't have it offhand. There will be basically a power factor, which will change the slope of this line. There's like a 2/3, I think, on there. We expect for gravitational waves in second space, I believe, to hit a power law index of 4.3. And then for strain space, it's in minus 2/3. And then we'll relate the amplitude of this power law referenced at 1 year. So we can see basically the strength of the power law we're starting to see, but we don't see the correlations yet. So The new update is in our recently released 15-year data set, which has about 20 more pulsars. We were able to extend that sky coverage and really start to nail down where these correlations lie. And for the very first time, we do see evidence for these Hellings and Downs correlations. So for the first time, we're able to claim evidence that we have seen gravitational waves from a stochastic background. So not only can we now measure this red noise process with the power law extending over many more frequencies, which with a higher degree of evidence, we also see the correlations. So the next question you may be asking deep in your mind is not only what did we see, but also how sure are we that we saw it? So for the Bayesians in the audience, the way we tend to measure this is, I've heard this called a Bayesigram, where we're comparing our different models and then saying how much do we prefer one over the other. The first that we'll compare is, okay, what if this noise is just coming intrinsically from the pulsars? It's actually just all random. They're all spinning, they're all quaking, they all have some red noise. And how likely do we think it is that there's actually this common spectrum process? So they all have that same spectrum that would indicate that there's an external process making the red noise. The Bayes factor between those two models is order 10 to the 12. Very, very high degree of confidence. We think this red noise process is common to all the pulsars. So then if we take that a step further and compare the model where there's common spectrum red noise, but it's uncorrelated, like those time correlations and those spatial correlations are not actually there, and we compare it to the Hellings and Downs correlations, we get a Bayes factor of 200. And depending on how many frequencies we model, that might change a little bit. There's more evidence in some frequencies than others. So at 5 frequencies, that Bayes factor goes up to about 1,000. Then we can compare some other more extreme models. So comparing some monopolar, dipolar correlations. Basically, none of those are preferred, which leads us to believe that, yes, okay, to a high Bayes factor, this Hellings and Downs correlation, that has a common spectrum red noise process, which indicates we're seeing evidence for gravitational waves, is by far preferred by the data. Okay. If you need more convincing, or perhaps, yeah, go ahead.
Sorry, in the previous slide, do you truncate it at dipole level, or do you also consider octopoles or other things like? And there's a question whether gravitational wave signal can lead to higher, modes or.
To my knowledge, I think we mostly end at quadrupole, but I have seen some analyses where they decompose into some more natural bases to look at any correlations beyond that, but I don't think there's any evidence, and that's why it's not presented
so
here.
Like a follow-up question could be that can you use principal component analysis or just like many pores,
Yeah.
Because, for instance, I'm just coming from black hole imaging kind of community, and if you just go to many higher modes, unfortunately, don't know the vanish.
Yeah.
So they all kind of turn on, if you have a complex structure.
Yeah, the one thing that one of my colleagues, Dr. Dusty Madison, has done is he's actually taken and done a principal component analysis and devised a basis that's based around, rather than a pure quadrupole, pure dipole, it's based around this Hellings and Downs as the 4th order basis. So then it provides like a more clear look to, okay, is it Hellings and Downs or is it something else? Is it something else quadrupolar that doesn't match? And that gives us a high degree of certainty that it does actually match with the Hellings and Downs. But I think to really dig into any of those further modes, we would really need more timing data. But that's probably something I might need to ask a colleague about. Yeah, thank you for the question. Okay, back to evidence. If you're not convinced by Bayes factors and you want another piece of evidence that we're very sure that this thing exists. So the next thing we do is we do a frequentist analysis where we generate many, many data sets that are seemingly uncorrelated and do not have the Hellings and Downs correlation. They just have intrinsic noise, or they just have an uncorrelated red noise process. And we see how often does our analysis think that there's correlations in this uncorrelated data set. And we can see it happens very, very rarely. So here, if we are pulling out a Bayes factor for those repeat trials, we get a sigma level of about 3 over many, many iterations. We have very few draws that actually reach that level that we have met. And then if we are doing a more frequentist analysis, we draw these many, many data sets, and then we run our frequentist analysis to see, okay, what is the actual signal-to-noise ratio of the background compared to the random noise in the pulsars. And here we hit about a 4 sigma level. Again, there are very few draws from that random generation that actually match that signal noise. And this relates to a p-value from between 10 to the minus 3 and 10 to the minus 4. So this was one of the more computationally expensive parts of this process, was not just doing this background search in the first place, but repeating it for thousands and thousands of data sets to actually see how often we could be tricked. The answer is very rarely. Okay, so that's the process. Now we actually wanted to say, okay, so we see this thing. What is it? We think it's gravitational waves, but what is the origin? I described the background using a supermassive black hole binary interpretation just because that's what's natural to me. I'm a binary astrophysicist. But there are other things that can cause stochastic backgrounds at these frequencies. So the first thing we did was we looked and said, okay, does it match with what we expect for supermassive black hole binaries? And generally the answer is yes, there is agreement, but it's not perfect. So you can see what we've measured in the 15-year data set here in blue versus what is actually generated from simulations of supermassive black hole binaries here in the red. And this is that gamma level of minus 4.33 where I've mentioned we expect binaries to lie. And we can see that the background that we have measured in the 15-year data set is a little bit flatter than we would expect for a binary signal, and it's quite strong. So while these two regions of simulations and data overlap, we expect them to be consistent. We really need more data to actually narrow in on the shape of this power law. If there's a turnover, making our measurements seem a little bit flatter, things like that to actually measure what is this thing coming from. So the next thing we looked at is what other physics can actually cause a stochastic gravitational wave background. And it turns out there are quite a few models that are able to be constrained at these frequencies. Things like cosmic inflation or scalar-induced gravitational waves, phase transitions, cosmic strings, domain walls, dark matter, many other things that are not my specialty, but I do want to show them because it really is important to show we're trying to consider every single thing that this thing can be. To say, what can we weigh in on, what do we need more data for, and how do we get the best data that we can to actually measure the differences between these models. So as you can see in this plot, many of these models are at very similar spectral indices down at our sensitivity level. So here we've recast these into a slightly different unit, so the shape is a little bit different. But here, the more data we get, the more we close these violins, we will be able to measure, okay, what's the difference between what we're seeing in each of these models more strongly. So again, it could be many of these things, but the important thing is we're one of the best experiments to actually reach this measurement level yet until next generation gravitational wave detectors come online. So hopefully we will be able to weigh in on what is out there. Okay. The next thing that is really important to remember is that NANOGrav is not alone. There are other pulsar timing arrays like us all across the world, and we also like to work together. So as we are contributing timing data from all of those 68 pulsars and more as we find more pulsars, so are they. And they're able to observe at times when we aren't, at seasons when we aren't. They're able to see more of the sky than we are, because maybe they're in the southern hemisphere. So by working together, we can both extend our observing baseline, increase our observing cadence, increase our number of pulsars, and overall get much more sensitivity to gravitational waves to study this landscape. So generally so far, what's really exciting is that everybody does actually agree. We're all starting to see a common spectrum process in our recent data set. The spectra more or less align. So as you can see here, NANOGrav is there in orange. The European pulsar timing array is in blue. Parkes pulsar timing array in Australia is in green, and a joint posterior here is in black. All of those overlap. They're all consistent, but they are starting to close more and more as we can make a better measurement with our data put together. So the goal is, in our next data release with the International Pulsar Timing Array, which should hopefully be coming up within the next few years, we're hoping that with a full timing combination, we can make a better and better measurement to both raise our sensitivity and our confidence level that we're seeing a gravitational wave background, but weigh in a little bit stronger about where it's coming from. So the goal is 25 minutes. I think I've gone a little bit over, but I think we're good. So I'll be able to linger a little bit on what is actually coming up next. So I mentioned that I'm a supermassive black hole binary astrophysicist. Most of my passion lies in searching for continuous gravitational waves from these individual binaries. And this is something that we do all the time as well, along with our background searches. And so on the 15-year data set, we unfortunately still have not seen any evidence for a continuous wave. It's probably made our lives easier as we were really focused on the background. Having to search for both would really complicate matters. But we can see our sensitivity to gravitational waves across the sky from these individual binaries is really starting to grow. We can limit a 10 to the 9 solar mass binary to about 160 megaparsecs on the most sensitive part of the sky where many of our pulsars are. And even within our less sensitive region, where there are fewer pulsars, we can limit it to about 40 megaparsecs. And we're looking all the time, and we can see on this plot all of those black points, as well as the big white points, are supermassive black hole binary candidates. So we're looking through this all the time. We're looking for these signatures, and we're also trying to help the electromagnetic community weigh in on where can we see them. The next thing that I'm particularly passionate about is combining those supermassive black hole binary electromagnetic models with the gravitational waves to do multi-messenger astrophysics. So I led the collaboration a few years ago in our first multi-messenger search, where we looked for the supermassive black hole binary candidate 3C66b. We did not find it, otherwise I would be giving you a different talk. But what we could do was place the most stringent mass limit to date. And while it's not yet able to rule out the electromagnetic model, we're starting to get very, very close. Here is our posterior limit on the mass from the 12.5-year data set. So we're starting to creep down, and we're gaining that sensitivity, especially on this less sensitive side of the sky, where we're learning that combining this data can actually make us more sensitive than just searching for gravitational waves alone. And I'll get into that more a little bit at lunch, so stay tuned. So I'll just end with the window to the gravitational wave universe is no longer just a few orders of magnitude wide. We have really blown it open to see much more of the spectrum. NANOGrav and other partners have found evidence for a gravitational wave background, but with new observatories and new efforts, we're expecting that evidence to grow over the next few years. And as next generation telescopes hunt for binaries, we're going to continue on our side to look for new gravitational wave signals to hopefully learn more about that binary universe. So exciting times are ahead. Thanks.
So I think there's a bunch of time for questions. Yeah. I think we're supposed to hand the mic around to people asking questions in case people online want to hear. Okay, so questions? Rosie first.
Yeah, wonderful talk. I have a question regarding to getting some ideas about the galaxy evolution and galaxy dynamics by hopefully resolving some of these binaries. Like if it had happened like at redshift of 2 or 3 or whatever, what do you think? Are we even getting close to that area of just, that precision data, or the next generation should give us that answer potentially?
So the unique complication of pulsar timing arrays is that they really are mostly sensitive to the local universe. It's not until we have this stochastic grown signal that we can really reach further. So for continuous waves, we're really looking, our limit is probably around z equals 1, which is quite local. But the thing that I do find really exciting is that as next generation surveys are looking for binary candidates or constraining evolution models, we can use those models to weigh in for what we expect the background to look like. So even if they're not a candidate for a continuous wave search, they might be something that can tell us, oh, we know this pinpoint exists. Hopefully that's representative of the population, and we can learn from that. So as we get more measurements and more candidates, we'll be able to learn and then go back and inform electromagnetic surveys about where is the best to look and what areas of parameter space we expect these binaries to lie in.
Okay, good. Yeah.
So what limits the current precision on pulsar timing?
A few things. So I can go back. I'm curious if I have this shape in here. This one will do. So there are a few things that make this characteristic shape. We typically represent it with a V, where the limit on the low frequency end is typically red noise limited. So currently that is the intrinsic red noise within the pulsars themselves. Eventually, when we're looking for continuous gravitational waves, we expect that will be the background, which is why joint modeling will become really, really important. At the high frequency end, where we actually expect many strong binary candidates to lie, the limit is white noise. So that's things like pure timing precision and the radio telescope precision. Every pulsar back-end pair has 3 different white noise terms that we model to do it as accurately as possible. So the more we learn about the pulsar timing models, so things like the way they spin down, the way they orbit, if they have any weird parameters that we need to know about and measure them more and more accurately, that will help us overall. That's also weighed in by the overall timing baseline, so how long we've been observing overall, the longest time span pulsars, as well as the cadence, particularly on our most sensitive pulsars. So the more we observe, the more sensitive we are, and that also weighs into what frequencies we can actually see.
Question?
Thank you, very interesting talk. The question may be a very naive one. That is, how could you exclude the hearing down? The cause of hearing down is not caused by the merge of the galaxy or by other gravitational disruption or perturbation events, but it's just the massive binary black hole. And how could you exclude? Because if you have the pulsars within our Milky Way, how do you exclude this kind of delay in the arrival time? It's not caused by some structure changing by our Milky Way itself.
Okay. I think I'll answer this in parts. So the first bit about how do we know that the Hellingsnauts come from a background rather than some other gravitational wave effect or other gravitational effect is, that's something we consider. This is why we thought it was really important to look for both continuous gravitational waves from a monochromatic signal, specifically from a binary, but that would capture some other models in there. And that would also be expected to give a Hellings and Downs correlation pattern if we naively looked for a background without looking for continuous waves first. We also look for things like bursts with memory and all of these other signals as we're doing this background search. That way we know, okay, if one of these other searches is ringing some alarm bells, we would go back to our background search and do that inclusive of these other models and say, okay, we know these things can induce these correlations, but they wouldn't necessarily induce the power law. So it's by seeing both together and making sure that they're consistent and consistent among all the pulsars that we actually build that evidence. And as for, if we're looking for just, the correlations in the pulsars, if there's something going on with the Milky Way, I might expect that to be semi-directional. And one thing that we were very careful to do was split our telescope data apart and make sure that we were seeing consistent results from both the Green Bank telescope and Arecibo. VLA is not timing enough pulsars that we can do just a VLA analysis yet. So what we did see was that all the pulsars in Green Bank and all the pulsars in Arecibo were seeing the same signal, albeit to less significance before we joined them together. So if we had only seen, Arecibo sees many pulsars on the side of the galactic center, but only within a narrow band, that might have also rung an alarm bell that this was not, a stochastic signal coming isotropically. The last thing that I'll mention that we do is we do look for anisotropies in the gravitational wave background. We expect it naively to be isotropic, coming from everywhere within, the local universe. But if we were able to see a hotspot, maybe that might indicate if that hotspot is half the sky, we might need to look for some other kind of a model. Or if it was a nice tight hotspot that's over a galaxy, that might be a place we want to look a little bit closer, looking for an individual binary.
Yes, I wondered how you, maybe you covered this just before I arrived, but there's a lot more pulsars than 50-something known. So are you carefully selecting the least noisy ones, or
Yeah.
is that how it goes? Because that could be a way of improving your red noise limit.
Yeah, so that's something that is done on a multitude of factors. So that's something that we do is we will try out a pulsar and add it in for a little bit, time it, and see if we can get it measured really well. And if it stays in, great, we keep it, new friend. And if it does not perform as we hoped, we might drop it and try a new one. So it's an iterative process as we're trying to optimize. The other complication, of course, is that we lost Arecibo, so all of those pulsars had to move to Green Bank to be timed, so time is a little bit more competitive. So growth might be a little bit slower over the next few years. But generally, you can reduce it to a few factors. One is the pure signal to noise of the pulse. The best timed pulsars are ones that have a sharp, strong, bright pulse over its baseline. So if it's something that's like a broad pulse profile or it has multiple components, that might add noise because our fitting might actually confuse different points in that pulse to fit as the pure time of arrival. There's also things like we are able to take binary pulsars. Most millisecond pulsars are in binaries. That's the other thing that's important to mention is we do exclusively use millisecond pulsars because we're looking for such short precisions. They're a much more stable rotator. That's something I neglected to mention, so thank you for asking. So we don't take any canonical pulsars. The other important thing is we don't take any globular cluster pulsars. These things have really complex accelerations that we might not be able to perfectly model within the timing model. So that might induce like a longer, slower process that we don't want to confuse for gravitational waves. So some people have done some searches using globular cluster millisecond pulsars to look for some other signals and made them their own like mini globular cluster array. But for our purposes, they tend to be not as well timed.
I did want to ask a couple of questions myself. So what is this bump in the sensitivity curve?
Oh, thank you for asking. Okay. The other thing that makes it really difficult to see a gravitational wave at a certain frequency is that the Earth is moving. So this frequency spike comes at a frequency of 1 per year. If we were to see a gravitational wave at a period of 1 year, it would be pretty hard to convince ourselves that it was real, and we were just not perfectly accounting for the motion of the Earth around the sun. So we lose a lot of sensitivity right there just because we actually have to account for the motion of the Earth in respect to Solar System Barycenter, to timer pulsars. There are a few other features that you can see that I personally really enjoy. Here is every 6 months, that's a parallax spike. The Earth has parallax. That is fit in the timing model to all of our pulsars. So we lose a bit of sensitivity there because it's a fit parameter. And then a few others of these, you can see these appear in some data sets and not in others. Some of those are actually pulsar binary spikes. So our most sensitive two pulsars are J1909 and J1713. Both of those are binaries and they have a very tight orbit that's very well fit. I'm not sure which is which. I believe it's those two that show up, which I think is the coolest thing, but like they're our most sensitive pulsars. If a gravitational wave showed up exactly at their orbital period, we might be suspicious. We would look a lot closer.
I'm going to ask one more question since I have the mic. There was this, there is some uncertainty about the power law index, right? So I'm really interested in understanding the gas-driven processes that bring these binary systems together. What do you think the uncertainty in the power law index could be indicative of a really early turnover? Or is that something that we've maybe ruled out already?
I certainly don't think a turnover is ruled out. I'll go back maybe to here. Maybe to this one. So I'm just going to come back to look with you. So the violins here, the bits in gray, are basically showing the posteriors for the amount of deviation from, you know, pure white noise that is in each of those frequency bins. And you can see that, like, while they're very closed and tight, that lowest one is a little bit lower than the fit power law. And there are a few features at higher frequencies that do end up tilting this a little bit. So as we have a longer timing baseline, a higher cadence, these disparate frequencies will be able to be separated a little bit closer together. So we'll be able to look for any particular features at those lowest frequencies. But as for right now, I think that a power law would basically be consistent with a flatter spectrum, just with the spectral resolution that we have. So I think the goal there will be, you know, as we add cadence and as we add timing baseline, that's what we're going to really be focusing on, is trying to, you know, break those frequencies apart to see as much of those features as we can.
Thanks. There were a couple more. Razzie?
Josh was saying.
I saw your hand up earlier, but okay.
No, I just had a question about the white noise
Yeah.
limit that you mentioned a couple of times. What is involved with that?
That has to do with, there are a few different factors that we include. The pure actual, like, timing noise we expect to be Gaussian. The pulsars do have some amount of, we call it pulse jitter, where the pulses, even though we model them as, you know, a perfect cone emitting from a pulsar, pulsars do all kinds of crazy things. They quake, they shift around, and that causes some intrinsic white noise. There's also white noise in the timing back end. So while we hope the electronics are as perfect as they can, we do account for a different white noise term between every pulsar and back end pair. So while we observe it at multiple radio frequencies to make sure we can account for all those effects and get all that wideband information, we do want to be careful that we're not inducing any systematic noise. So things like electron noise and just that receiver noise.
Razzie?
In the slide that you compared the data with the theory, can you go back to that? I have a few questions about this.
Is it this one?
Yeah, so firstly, why do you have so much of the, I feel like that in your red one, which is like a simulations, there's almost certainly another few parameters that are controlling those that you haven't shown. So I want to know what are those things, and related to that from the data side, could that be that it also has the the unavailability of probing much lower signal? Could that be related to the sensitivity of your experiment, or the fact that you just need to wait more time, that you just increase the signal to noise data by just like, by increasing the integration time? So which one it is, like, because they're obviously not similar to each other.
Yeah, okay. I'm going to start with your second one just because I wanted to ask a clarification. So the blue one is a measurement. So we do see that those contours close, and we see like that is the two parameters of the power law that we are seeing. However, you notice that compared to the binary models, it is quite loud. So the vertical axis is the amplitude of that power law. So basically scaling that could be either, more binaries, more massive binaries, a louder overall background. So while this is the measurement we're getting, it is important to know that, with that timing baseline, we, expect those contours to close. They could also shift. But we do want to learn about why we are measuring such a loud background. Does that have to do with the binary population or the gravitational wave population? Is it because we're seeing a mix of signals from two different sources? All kinds of things, and that will come with the spectral resolution. Does that answer your question?
Yeah, well, the question that I had was that why you don't see lower things, like, why you're almost like 3 orders of magnitude above the lower limits that the simulations propose. So does it have anything to do with the sensitivity that you cannot really probe down to -16 in log of the amplitude, or Does it have to do with the fact that it's just only 15 years of data? If you go to 30 years, could that be that you can just probe, lower ones by increasing the, integration time for the detection?
Got it. Yeah, I see what you're asking. So, I think I'll flip the question and say it has to do with, the sensitivity of where our array is at, that we are able to measure the amplitude that this background is at. If it were quieter, we might not have seen it yet. We might have needed more data. But I do agree, as we are looking for those resolutions, if it's just a single power law, we're going to keep measuring that power law at the amplitude that it's at. Even if we are more and more sensitive, it will just help us constrain those parameters better. We won't be able to necessarily see under it. So, but there has been work done that's attempting to optimize our ability to disentangle, for example, two different power laws, maybe a binary background and an inflationary background. So that completely just depends on if one power law is dominating over the other. If they happen to match up just right, I think there's ways to look for a break in the spectrum. And that would come with sensitivity. We would need to actually be sensitive enough to see that power law sticking up above our intrinsic pulsar red noise that we can measure better and better with a longer time span.
Okay, and regarding to the first question, what drives those contours from the simulation side? Would that be other parameter that you need to feed the data for?
So these, I think, end up extrapolated from, you generate a binary population and then you actually integrate all their signals up to reduce it to a power law background. So it will have an amplitude and a spectral index. Of course, when you have those simulations that are made of individual binaries, there are other things that you can look at, like the average mass or distance, or if there are any outliers from an average power law background. So those are parameters that can be fit, but they, I think, would need to be fit with other searches. Here we're basically trying to say, okay, we have this population, what would it look like in this search for a power law background? But we can use them to inform some of our strategies to say, okay, the ones that match the best, they have lots of strong binaries that peak up above the signal. Maybe we want to really throw a lot of effort into looking for continuous waves. Or, this is something that I'm not 100% sure of, so I'm speculating with you, is, or on the other hand, if the strongest backgrounds that match the best are ones where they're, very uniform and isotropic, that would also inform. But that's not something that we can see just from this. We would have to go look at the individual simulations to see what fits the best.
Maybe one last question?
I remember Joe Taylor giving a talk in this room many, many years ago, and he said that the largest uncertainty in the spin down of the orbit of the binary black hole was the solar acceleration in its orbit around the galaxy. Mm. So I would assume that's been a lot more better measured now from the pulsars. But
yeah, that's something where that comes into. This is my guess here. This is part of why we look for these other correlation patterns. If we, for example, saw a big dipolar correlation, that's something that I would expect would match with, an acceleration of the sun around the galaxy, the Earth around the sun, some kind of motion. We're moving in a direction. So this is why we find it really important not just to look for a pure monopole or dipole, but we look for a Hellingston-Downs plus dipole or a Hellingston-Downs plus monopole to make sure we account for every combination. And if we see something unexpected, we go take it out. This kind of relates to something that happened with our 11-year data set. We started to see some correlations that didn't quite make sense. And we actually found that it was due to the need to model the location and mass of Jupiter more accurately. It was coming up at a period of 1/11 years, which we were like, that looks familiar. So for a while, we actually had to include that in our Bayesian model. Now Juno is there and can tell us exactly where Jupiter is, so that's very helpful for us. We don't have to model it separately anymore. But we do continue to, as we're looking at this, we're constantly running those consistency checks of, okay, does this look like something else? Does it fit best with gravitational waves only, or some other thing that we can then go model?
Okay, I'm going to ask one last question, actually, because I remembered it now. So you said that in terms of the continuous wave population that we might be able to measure, this is not going to be a super large population that we can probe. But do you think it's going to be the way that we're lucky to see one, or in a few years we might see dozens? Well, I mean, it would be really cool, but can we?
So I would be surprised if it hit dozens. I'm much more in the camp of like, I really hope we get one. Because it will need to be close, it will need to be loud. I have done some work, and I think there's been more work done since I did this, on modeling 2 continuous waves in the same data set. And I'll just say it's really hard. When we're doing these pulsar searches, we model the white noise beforehand, so we fix that a priori. And then we search for 2 red noise terms in each pulsar plus the gravitational wave signal. So that's 2 times n pulsar, which is 68, so that's over 100 already. And then you add in gravitational waves. A background is just 2 parameters, so that runs pretty fast. When you get into continuous waves, you actually have 2 more parameters per pulsar, because the signal for a continuous wave is different at the pulsar than Earth. If somebody wants to hear more about that, please ask me. I can go on about it forever. But, so we model that, so that's double the number of parameters already. And then you have an 8-parameter continuous wave. So when you double that, it's really hard, and one can easily mask the other if you're not careful about removing it. This is something that I think we can really learn from other communities. People are thinking about this for observatories like LISA, where they're trying to maximize how to do a global fit. We, I think, can really inform each other on the best way to do that if we do hit that situation. What I'm thinking about more currently is how to jointly fit a background in a continuous wave and how those might bias each other. That's what I've been working on a lot in the background, is like thinking how to move beyond this and be a step ahead of the data and make sure that we will not induce any bias into our parameter estimation.
Okay, so let's thank Caitlin for a really fantastic talk and a very strenuous discussion. Thank you. And Caitlin is also giving the first lunch talk, so you should stick around.
Thank you for the questions.
That's great. You tired?
I'm good.